initiate the first lecture of the distinguished lecture series, which was originated 2 years ago. Once again, it's a distinguished lecture series for all member institutions for IMSAC. And we are very grateful today to have in Miami as one of our distinguished lecture series speaker, Andrés Navas from University of Santiago, Chile, and Professor Navas is an expert on ergodic theory, dynamical system, and geometric group theory. So he studied in Congo in Lyon under Etienne Kiss, and for his achievements in mathematics, he was awarded Atlantic Congress of America Prize and other awards as well. So we're very grateful to have Professor Navas, who's going to talk about Arc-Connectedness of the space at 1D commuting diffeomorphisms. Andrés?
Okay, so thank you very much. Thank you very much for this kind invitation to Miami. This is my first time. And actually, you mentioned many areas of mathematics, but in this talk there will be a lot of analysis, but very elementary analysis. And I should add that most what I will present is joint collaboration with Hélène Eynard from Institute Fourier in Grenoble. So I will try to present this result that we recently obtained with Hélène, which is a kind of technical one, but what I want to emphasize is why this result is interesting, what are the difficulties in proving this, and I will not go into the proof. This is not my goal is just explaining why this was solved for many years, and it is so hard to do something in this study of commuting diffeomorphisms. So let me just start by saying that the talk will be about group actions, but so let me just say that over the last year there has been a lot of activity in the study of group actions with no kind of invariant structure, so just actions by diffeomorphism of manifolds. So you take an abstract group and you look at all possible actions of this group on the manifold, and this is inspired by many issues, problems in loop theory, problems in formation theory, problems in topology, etc. And many important results that have been obtained recently, as for instance the solution of very important conjecture by so many important stuff on this deal with obstructions, which means that because of the algebraic structure of the group, it is impossible to look at. So there is no action at all, or in some cases all the actions have to respect some properties. So there are dynamical constraints for the actions. Let me illustrate this with a kind of elementary theorem from the 70s that I like very much. The proof is not very hard. This is inspired by the thesis of Nancy Coppell, who was a student of Smale. And the example says that you take an important group of C2 diffeomorphism of a one manifold, the circle, the interval, the real line. It is important, then it is abelian. Okay, this is the theorem of Blanc vectors, which is a kind of very and how the starting point for the study of the issues related to differentiability for actions on one manifold. And the warning is that this is widely false in class C. So in class C1, every nilpotent group which is torsion-free appears as a group of C1 diffeomorphism of the interval.
So, but do you assume torsion-free in the first theorem?
No, I don't assume.
So it cannot be an extension of.
Sorry. Of course, yes. Okay. This is true for the interval. Thank you. And for the case of the circle, no, because the confusion is just it's abelian. No, I don't assume it's okay. gonna see this section. I think it is not explicitly written in the paper of Thorson, but there is another paper by much more recent by Fag and friends that deal with the case of the circle and the real line. So they just stated the theorem for the case of the internet. And of course, Thorson was interested in problems coming from Fourier theory, because when you have a group action, you can take the kind of this procedure of suspension and you get a Fourier, and depending on the dynamics of the group actions, you get different properties for the topology of the Fourier, etc. So in that case, if we think about two commuting maps, okay, so I will come back to this point. But this is very interesting. So this is why we also interesting. Every important group, at least every torsion important group, is in there, but no non-abelian important group is in the group of C2 diffeomorphisms. Okay. Okay. So my goal is to speak about go in another direction. So I will speak about groups that do act, and I will try to classify actions. So I will not look for abstractions, but I will just take the space of actions, and I will try to say about something about it. And there are many points of view to deal with this. So for instance, if you take maps at random to generic diffeomorphisms, well, from the point of view of group theory, this is not very interesting because in general they will generate a figure. Okay, this is kind of exercise using the topology in the space of diffeomorphisms and their category arguments. So you take two diffeomorphisms at random, two homomorphisms at random, and they will generate a figure. And there are many extensions.
So this is the father of the Google owner?
The father?
Of the Google owner?
So, yeah.
There's this Misha Brin, but I'm not sure it's spelled like that.
So, no, this Brin is Matthew Brin. It's another Brin. Yeah. Okay, so there is this one in there. So if you take two piecewise affine homomorphism of the interval, this is a very nice stuff. Tricky argument by classical argument by Brin and Skep from the 80s. They will never generate a figure. So there are some constraints there. So here the point is that in the group of piecewise affine homomorphism, there is no topology, no good topology actually. I mean, this bare argument, bare category argument doesn't work, and actually we have. Okay, another point of view. If you so I will restrict to the case of commuting diffeomorphisms, and again there is this generic point of view. Take a diffeomorphism at random and look for the set of diffeomorphisms that commute with this limit. So this is classical stuff in dynamics. I think the first in getting deep results on this was Smail and Nancy Koppel. So she dealt with a one-dimensional case. That was actually her thesis. And then there was work by Paris, of course, and very nice result by Bonatito, Ricci, and Wilkinson concerning a conjecture by Ismail.
So this covers some years, like 30, 40 years.
Yeah. So this is from the 60s. I think this is in the early 70s. This is, I guess, 10 years ago. Okay, but actually, I am not specifying here the regularity, because you can ask this question in the group of diffeomorphisms of class C1, C2, C3, and so on, and in each regularity, you really need a different kind of argument. So, for instance, this work were in class at least C2, and this is in class C1. And it's really amazing because the result is the same. So generically, the centralizer of a diffeomorphism is very small. It's just the powers of the diffeomorphism. This was proved by Paris and your course in class C2. And the proof of Bonatito, Ricci, and Wilkinson works in class C1, and it's somehow the opposite. But the result is the same. So So here there is a property which is called control of distortion in dynamics that makes that gives the rigidity, and amazingly, it is the lack of control of distortion that gives the rigidity as well. So, but the point here that I want to stress is that if you take the generic point of view, you get things that are quite reasonable, but you don't get really a structure. So I really want to study a space of commuting diffeomorphisms, and this is inspired by problems in population theory. So if you take two commuting diffeomorphisms, because of this procedure of suspension, you can create a population. For instance, if you take two commuting diffeomorphism of the circle, you can take a population on the torus times the circle, and you would like to study the deformation of this solution, and this is related to the structure of the space of commuting diffeomorphisms. And the first thing is that studying the space of diffeomorphisms is already a very important stuff in topology. And there is this theorem of Smith, for instance, that says that if you take the space of diffeomorphism of the sphere, it has the same homotopy type as the group of rotations, which there is an important so there is an extension by factor, and the later one, very important, the later one in dimension 4 by Watanabe. And so the issue here, even for a single map, is not that easy. But I want to take this example here, what is called the Alexander trick, because it's going to be important for what. So the example is that if you take a ball, then the space of homeomorphism is contracted. And the group is very simple, so you take the ball and you renormalize the ball so that it becomes smaller and smaller. And you conjugate the action, and so this gives you an action on a smaller ball, but you extend this action as the identity outside.
So is it true that if you go from C2 to C3, then it gets simpler, or it's more complicated?
For what case?
Well, in general, if you increase the
if you increase the regularity, so there is a kind of philosophy. C1 is very special because C1 is too large. It is very easy to build C1 diffeomorphism. If you get something which is true in class C2, then it should be true in high regularity. This is more or less the philosophy. Okay? Because in class C2 there are other important tools in dynamics which are called control of distortion. And whenever you manage to get control of distortion, then you should be able to do it.
The proof you mentioned for Alexander, the example of Alexander seems very simple, but there must be a catch somewhere.
Yeah, the point is that you're only dealing with homeomorphisms. If you take two diffeomorphisms and you implement the deformation, there is no continuity for the derivative. So in the limit, you collapse it. Okay, but it is something very simple and elementary that gives you some intuition of what's really happening. Okay, so for instance, if you take two commuting homeomorphisms of the interval, then you can use the Alexander trick. In the limit, you get that real action. But if you start with two C1 commuting diffeomorphisms, it doesn't work because of the lack of continuity of the definition. And it doesn't work as well for the case of commuting diffeomorphism of the circle. Okay? And actually, I should say that concerning the structure of commuting diffeomorphism, almost nothing is known, even in dimension 1. And there is a very old question from the 70s by Harold Rosenberg, who asked whether this space is path connected. It's locally path connected. Okay? And this was inspiring in some sense by the results of Hermann at that time about linearization of circle diffeomorphisms. So Hermann solved a very important conjecture by Arnaud, It was treated by Yokos in his thesis. He mentions this explicitly as a motivation for this, and he really thought about this during his life. So it is a C local. So Rosenberg didn't specify the regularity for this question. This is another issue. And what I will present here is a solution for this, just for the path connectedness, not for the local path connectedness. This remains a mystery. And it's a kind of very difficult problem. Many people talk about this, and I will try to explain.
Sorry, I missed that. This is this American who lived in Paris.
Yeah. Actually, he was the advisor of Michel Herman. Yeah, at that time he did topology, and then he did a little bit of dynamics, and then he moved to Europe.
Yeah, I know.
Yeah, but okay. So the theorem that we proved with Hélène Eynard-Bontemps and Grenoble is that at least the space of commuting diffeomorphism of the circle of the interval is path connected. In this very special class of differentiability, I will explain some issues concerning this. This is not exactly C2. This is C1 plus absolutely continuous, which means that derivatives have absolutely continuous differential. The derivative, yeah. No, the derivative is absolutely continuous. So there is a second derivative in the space L1. Okay? And again, I will try to explain why. So the proof doesn't work for C2, our proof. In case C2, it only gives connectedness, but not path connectedness. And but what is important here is that we get a differentiability very close to C2. So now we are more or less convinced that this should be true in any regularity because of this. This is what I mentioned. Let me just say that this is not to be true in class C1. I proved this 10 years ago, but in class C1 the situation is different. Actually, the proof is much easier, and it is less interesting because in class C1 it is very easy to construct diffeomorphisms, and it's very easy to construct commuting diffeomorphisms. So you want some deformation, so it is not very hard. Okay, and there are many related results, but actually, so this is a list of results that were already known. All of them are very specific concerning the regularity, what is exactly the result. So for instance, this very nice result by Bonatti and Hélène Eynard again, they proved 10 years ago that the space of commuting diffeomorphism of the interval in class C is connected. And this is already very hard. Technically, this is very hard. They use a classical construction by Girard from the 70s. And this is what I mentioned before, that it was already known for commuting C1 diffeomorphisms, but this is not very interesting. But in the case of C1 diffeomorphism, there is another issue concerning loop structure. So this is true for nipotic group actions. For the case of nipotic group action for C1 diffeomorphisms, it's also path connected. And this is not true in the solvable case. So many things can be said about this, but I want to go into the core of the thing. So the first thing is that this is related to problems in collisions, and the second thing is why I want to emphasize what is the difficulty in proving this kind of things. Okay, and okay, so there are two naive approaches to this problem. So the first one is try to use the Alexander trick, but as I already mentioned, it doesn't preserve regularity, so there is no hope to get some connectedness preserving the regularity. So. And the other thing is that maybe Let me draw a picture here. So suppose that we are in the case of dimension 1, and I take one map, one diffeomorphism. So one diffeomorphism is just a graph like this, and there is a canonical way to deform this map to get in the limit identity. It's just moving the graph in a linear way, so that in the limit it becomes identity. Okay, so this is somehow a variation of the Alexander tree. The problem with this is that if you start with two commuting maps and you deform them, so there is no hope in general that in the middle the maps you obtain will commute. So this is not a deformation of in the space of commuting diffeomorphisms. So it doesn't work. But there are many results giving a structure for actions of commuting diffeomorphisms. For instance, it's a classical theory by Danjois, Poincaré and Danjois. But if you take two diffeomorphism of the circle, if you take a simple diffeomorphism with the non-periodic point, then it is actually a rotation up to a conjugacy, up to a change of coordinates. So this is a very important theorem by Danjois. And so Danjois proved for a single diffeomorphism, but it works perfectly for the case of commuting diffeomorphisms. So if you take two commuting diffeomorphisms of class at least C2 or C1 plus absolutely continuous, or whatever, then there is a simultaneous conjugacy to the rotation. So a natural thing to do in this case, if there is no periodic point at all, is to have the action, but actually have to change of coordinates. The action is an action by rotation. You would like to just change the to do a path along the change of coordinates to get an action by rotations in the limit. But the problem is that this is very well known, and this is very important stuff in this framework, is that the conjugacy you get in general is not smooth. It is related to problems concerning small denominators, and it was cleverly pointed out by Arnold in a classical paper about small denominators. And there are many very important work by many people on this. But the point is that in general the conjugacy is not smooth. So you have an action, the action is actually an action by rotations, but you cannot change coordinates because the change of coordinates is not smooth. So you will never get path connectedness using the coordinates, using change of coordinates. And there is something similar for the case of the interval. This is again, there is a lot of analysis in here. I am killing this part, but this is somehow technical, but very interesting. So if you take a diffeomorphism of the interval, say a diffeomorphism with no fixed point, so the diffeomorphism is quite boring from the point of view of dynamics, so it moves everything to the right or to the left. Well, there is a famous construction by Sequeres, later improved by Sergerard, that says that it comes from a vector field. There is a unique vector field actually, which is a class C1, for which this mapper is the time one of the flow. And if you take two commuting diffeomorphisms, the vector field is the same. So you have to change the time to get the two diffeomorphisms, but somehow there is uniqueness of the vector. But the problem here, and this was cleverly noticed by Sergerard, this is technical, but it really happens, is that the flow is not more regular than C1. So you take a C2 diffeomorphism, you get a flow which is C1, but no more than C1. And at the corresponding times of the diffeomorphism, you know it is C2, but in other times it is only C1. And actually this is what happens in general. Okay, so this is very nice. So one can create, and again, this is an exercise in analysis. One can create a diffeomorphism of the interval with no fixed point in the interior, which is a class C2. It has a square root, which is a class C1, but the square root is not a class C2. Okay, you can play a lot, so you have a master on this. And Hélène had, and together also, here I should add also the name of Diffeomorphism. They became very enthusiastic in building new examples of many strange things that may happen. So you can have two diffeomorphisms of class C2 that commute, that are somehow independent between them, in the sense that the translations are independent. So any combination of them gives a C2 diffeomorphism, but the other diffeomorphisms that appear in the flow are not C2, just C1. Sometimes they are slightly better than C1, but not C2. Okay, so again, there are serious problems like this. So this is classical stuff. This is from the 70s, and this is why it was known that the question of the connectedness was difficult, because each time you try to use the result that were available, well, what you get actually is a kind of obstruction. So you cannot move the action to get from it. And so what is the idea to here? If you look on the internet, this was 10 years ago. It's a fantastic presentation by Hélène Eynard about her construction of very exotic vector fields on the internet. And there is still another problem concerning the interval. So if you take I will come back. So I stated the previous result for diffeomorphism of this interval, which is how close it, how open. Actually, if you close the interval, and there is another problem that was studied by Grenoble, is that the theorem is no longer true. So the existence of a C1 vector field. What happens is that there is a vector field on the left and there is a vector field on the right, but these two vector fields are not necessarily the same. And the non-coincidence of the vector fields was studied by your mother. She created an invariant on this, which is called the mother invariant, which was later studied by your course, because he didn't really write the main results concerning this. And the point is that they made it deep. So, and there is something deep inside. So again, there are many. And here there is the abstraction comes from this non-coincidence of the something which is called the mother invariant. Okay, and what I want to emphasize is the idea that we have. So the idea is not using the coordinates that are given by the conjugacy results or the vector fields, because these coordinates may be bad. But something very simple. So you start with the action and you try to conjugate. You have always the same action, but you try to conjugate by a path of different. And you want to get in the limit, for the case of the circle, for instance, an action by rotation. Okay? And if, for instance, suppose, so here there should be, there's a mistake here, this should be G. So, okay. And it turns out that this is doable. In C0 topology, this is doable. In C1 topology, there is an obstruction, but we can manage to understand the obstruction, and we know what to do in that case. And what we did with Hélène is that we detected the obstruction also in class C1 but absolutely continuous, and we managed to to control. So this kind of idea seems to work always, but it needs more work, but this is the point. So, and well, this is very natural to think. It is very natural to expect that this works in C0 topology, because in C0 topology we have somehow the coordinates that for which f and g become something like rotations. This is not exactly true, but anyway. And the difficulty appears when you look at the derivative. So may I use the blackboard? No? Yes?
Yes, yes.
So I will do just one calculation to show what is the case. So I will do this, but only with one mark. So take homeomorphism. So this is this kind of exercise. Take a homeomorphism of the circle that preserves the orientation, and I will conjugate it so that it becomes very close to the rotation in C0 topology. And the idea is very simple. So you take Hn is just the sum of x plus f of x plus f squared of x plus this. Of course, these are maps of the circle, so I will take a lift of f to the real line, and it will perform this consumption on the real line. Okay, and now there is the classical case. So I will take Hn of f of x. This is 1 over n, and then I have to replace x by f of x. So we have this. Okay, and now I will look at the difference between these two expressions. So this is a classical case. So this is 1 over n f to the n of x minus x. Okay? And this, for a circle homeomorphic, converts to something which is called the translation number of f. Okay, this is the work of Poincaré. This is classical standard. Orbits move at a linear rate. So this is saying that Hn of f is very close to Hn composed with a translation on the left hand, with a translation. And this descends to the circle, so Hn is very close to the rotation by what is called the rotation number of f, which is just this related to the circle, composed with, here there is something. No, sorry. This is composed with Hn, because you move this to the right, and this is more or less Hn plus this number. So this is very close to this, so that when you move to the circle, which is exactly Hn composed with f, composed with the Hn inverse, very close to the rotation. And this is a kind of Alexander trick at the level of the action. Okay. You don't renormalize the space. You renormalize the action. This is the only argument that it is involved in. Now the point is that you can do exactly the same when you have two commuting maps. Then the homomorphism you have to take is the sum along the orbits of the two maps. So I can erase this. So I have to replace for f and g, I have to replace Hn by a new Hn, I will denote this way, 1 over n to the square, the sum from 0 to n minus 1, I and j, f to the power I, g to the power j of x. Okay? And it works because of the commutator. Just perform the same. So this gives a proof in the C0 case. And what we want to do is that in the regular case, we don't want to take this expression and compute derivatives because this is very, very hard. The derivative of this, so the first derivative of this, and so on, so very often. But we would like to do the same at the level of derivatives, in the sense that instead of taking f, I will take the derivative of f, and I will try to perform such an argument for the derivative. Okay? And this can be done in class C1. Well, here there is a trick. Not a trick, but there is something important. There will be a term that you need to control. And in this case, this is the translation number. And what we want to do is something similar. So let me again take a explicit formula for this. Now take a C1 diffeomorphism, and I want to build a conjugacy. But instead of building the conjugacy, I will build the derivative of the conjugacy. And the derivative of the conjugacy, so I can give the derivative, but it's better to give the logarithm of the derivative because it satisfies a chain rule. And this is very close to what I wrote before. This is 1 over n, the sum from I to n minus 1, the logarithm of the derivative of f to the power I of x. Again, this is a kind of check argument. And it works. It works in the sense that hn composed with f composed with hn inverse converts in C1 topology now to the rotation if, and actually this is an if and only if there is the obstruction that appears, if and only if the growth of the derivative is sublinear, which means that the logarithm of d to the fn divided by n in C0 topology goes to 0. Okay? Which is this is encoded. It's easy to show that this is encoded by the non-existence of hyperbolic periodic points. So again, the idea is the same. Instead of taking means of the action, you take the means of the derivatives. And the point is that we have detected the obstruction to make this argument work. But this obstruction is easy to handle because in case where there are hyperbolic periodic points, and this is important, what we can do if you take something like hyperbolic periodic points and you conjugate by the map, by this map, which is just Holder but not class C1, this transforms into again a hyperbolic periodic point, but the multiplier changes. So we perform this conjugacy here in this case. So the map we are conjugating, we are using to conjugate is no longer C1, but the path of diffeomorphism is still C1. Okay? And the proof uses the property, the additive property of the logarithm of the derivative. The important fact is that it is a cocycle, which is just the chain rule. And what we did with Hélène is just to go from class C1 to very close to C2, to C1 plus absolutely continuous, is to use the affine derivative and to use the corresponding chain rule for the affine derivative. So the affine derivative is the derivative of the logarithm derivative, which is d2 over d. And d2 over d is related to something which is important there is also the Chaucian derivative regularity and so on, but what is important is that it has a dynamical content. So the L1 norm of the affine derivative, which is just the affine derivative of f. Well, this is the integral of the absolute value of the derivative of the logarithm derivative of f. And what this is the because of the formula. This is the variation of the logarithm of f. Okay, and this is a very important number that was introduced by Danjois. Okay, so he really realized that in case this number is finite, these arguments of conjugate distortion that allow to give some information about the action. And what we need to do now, this is the same as in the case of continuous action and regular actions, and C1, is to look at this number. What happens with this, with the growth of this number for the iterates? And this is what we call the asymptotic variation of the diffeomorphism. So we don't look at directly at the variation of the logarithm of the derivative, but at the behavior of the variation of the logarithm of the derivative along the iterates. If this number vanishes, then we can repeat the argument in class because of the same kind of because of the same kind of arguments of taking means along the orbits and so on. But the point is that this number does not necessarily match. This is the key tool for the work. Okay, so we wrote a very long paper on this just to understand what is this number, and the question was, what about the case where this is positive? Okay, but for that there are two structural results. So the first result is that in the case of the circle, when the rotation number is irrational, I prove that this number vanishes. Okay, which is somehow related to classical work on circle diffeomorphism. So this is not very surprising. What is surprising here maybe is the fact that the proof is elementary, but it is not dynamical. I mean, this is really analysis, and there is an issue here that the result is, if you look at the number at the asymptotic behavior of the variation of the logarithm of the derivative, then it is true in class C1 plus absolutely continuous, but false in this class C1 plus only variation, which is the class of the theorem of the Landgraf theorem. So there is something which seems to be technical, but it is not that technical. I mean, there is something interesting related to the work of the model. It only arises in this specific class of differential. But the point is that for the case of irrational rotation, this number vanishes. So we are in the good situation, and the case of rational rotation number is essentially the case of diffeomorphism of the interval. So you can reduce that case, the case of diffeomorphism of the interval. And again, what we did prior to proof of connectedness is to understand what is the situation here. So, and the theorem is that if you take a C2 circle diffeomorphism, diffeomorphism of the interval, a C2 diffeomorphism of the interval, then this number, the asymptotic variation, is positive, which is the bad case for connectedness. If and only if, and this is what we did with the length. What I mentioned before, the mother invariant of f is non-trivial. So there is a kind of black box here. So this is mother's invariant. And the point is that because of the work of Mother and Yokos, the centralizer of f is generated by a single map, which is not necessarily f. It may be a root of f, but it is generated by a single map. Okay. So you can forget about this. So this is the important point: is that because this theory was already available and we related this number to the mother invariant, we know that if this number is positive, then the centralized is generated by a single. This is the way to look at it. Okay, and there are many issues in this, but the point is that, well, we cannot use the trick of the conjugacy trick to get an action by rotations in the limit because of this. Nevertheless, we know that in this bad case, the centralized is generated by a single map. And since it is generated by a single map, we can perform the Alexander trick at the level of the graph, because we only need to define one map. We don't have two maps to deformate simultaneously, so we can deformate the graph, and this gives you a right deformation. Okay, so essentially this is the strategy. As you can see, there are many technical issues along the proof. So but in general, all of this, the analysis that is involved here is quite elementary, and this is what we discussed with Hélène. So everything was available in the sense. But the point is that this notion, the introduction of this notion was essential to understand what happens with it. Okay, this is the notion that gives you the key to go through.
Are these abstractions independent in general?
No, that's a very good question. So if there is an hyperbolic periodic point, then this number is positive. Okay. Sorry, this is not true. Thank you. Thank you. Yeah, this is implicit in this statement. So this is the difficult case, the case of parabolic exponent, because in the case of hyperbolic exponent, I can use this conjugacy trick with the x to the alpha and kill hyperbolicity. It doesn't work like that. Anything works as I'm telling you, because there are always some technical issues involved, but this is the idea. So the difficult case is that of parabolic exponents. But in this case, this holds. And if you have an hyperbolic exponent, then this number is automatically positive because of the growth of the derivative at this point. So this contains the abstraction implicit. Second level abstraction. And of course, if you want to go into higher regularity, this is a question that I wrote last week. So this works very, very, very kindly because of these cocycle relations. But there is another cocycle in class C3, which is the Strassen derivative. And you will very hard try to do the same thing using the Strassen derivative to go to class C3 and to construct some kind of cocycles in high regularity and to perform the same tricks. And we are working on this now. We are somehow optimistic, but it's not that easy. But of course, the next step, instead of going to class 3, I think we should go directly to simple case. Get control. In many cases, this is simpler because what is nice with the result is that you don't lose regularity along the path. So in many situations in this context, there are theorems where you lose some regularity. For instance, you take the linearization of circle diffeomorphism. The classical theory says that there is a conjugacy which is smooth when there is different kind of notation number, but the conjugacy is slightly weaker than the linear diffeomorphism. But here there is no loss of regularity. But if you are in class infinite, you can use high regularity to control the smaller number. So it should work. Okay. So I think I will stop here because I'm running out of time. Thank you very much.